One of the main reasons that we use Boolean algebra is to simplify equations, or in other words, reduce them to a minimum number of terms. Most typically, when we talk about simplifying or minimizing equations, those terms mean the same thing, minimize or simplifying, we mean to reduce an equation to the minimal sum of products form, or a minimal SOP form. This is opposed to the canonical SOP form that we talked about when we use min terms. So the canonical SOP form is when the SOP form has only min terms in it. The minimal SOP form has products still, is a sum of products, but those products can be minimized. So for example, here's a minimized SOP form of an equation. So it's still a sum, an OR of products. Here are products. Still an OR of AND terms, or a sum of products, but these product terms can be minimized. They don't have to be min terms. So remember, an implicant is a product of literals, and a literal is a variable or its complement. And so simplifying could also mean using fewer gates. So reducing the number of gates, lowering the cost, lowering the power, etc. So for example, y equals a, x, or b, y equals a, x, or b is likely simpler than the sum of products or SOP form of the equation y equals a, b bar, or a bar b. So these trade-offs, cost, power, number of gates, depend on the technology. So let's take, for example, simplifying this Boolean equation, y equals a bar b or ab. Well, we'd simply use combining and get to y equals b. So this reduces the number of gates, gets us into, this is the minimized SOP form of that equation. We could have also used other theorems. Combining is the simplest one, so recommended. But here's another way, if you happen to not see that, factor out the b, for example, get a or a bar, use complements to make that, turn that into a or a bar into 1, and then b and 1 is just equal to b using identity. So again, recommended, but there are usually, just like in regular algebra, several different ways to get to the same result. The most important thing is that if you're applying the theorems correctly, you'll get to the same end result either way. Here's another example of simplifying Boolean equations. So let's say we start with this sum of products form, canonical sum of products form, assuming y is some function of a, b, and c. And so we could see that looking at this equation, we always want to look for combining and covering. Those are two that we want to look for, where combining is y equals a, b, or a, b bar equals a. And covering is y equals a, or a and whatever, right? D. This is just equal to a, right? This is like saying, well, you can go to the yurt if you have an apple, or if you have an apple and no banana, and a cat, and a dog, and an elephant, and 5 frogs, and a goat, right? Okay, it doesn't matter, right? You can go to the yurt if you have an apple. This is a more constrained case, right? An apple and a bunch of other things. Well, guess what? We already have this a or in that term, and so that just reduces to a. That already covers, this first term a already covered this case, right? The more constrained case. And so we can look for, in this case, we're going to look for combining or covering, but combining. So we could actually combine these two terms because they differ only in a single term. Had they differed in more than one term, we can't combine them. But these differ only in the b term, and so we can combine those. And it turns out we could also combine these two because they differ only in the a term. And so, well, can I use that a and b and c term twice? Sure. Right, and I can even duplicate it using idempotency. A and b and c, I basically replace that with two of those, A, B, C, or A, B, C. And now I can use combining for both of those. And I see that these differ again only in B, and these differ only in A. And so we're going to get whatever left out of that, A and C, or B and C. And so this is now the minimized SOP form, sum of products form of the equation.